morning, everybody. For this presentation, I will be helped by Jonas Bernardon and Hakim Benegou, excuse me, from Onet Technology, Comex Nuclear Company. We will present you the activity of the replacement of the pressuriser immersion heater. Please excuse my diction in English. First of all, we will see the EDF requirements. After that, the EDF organization for ALARA principle. Then we will present you the intervention. We will have a look at the initial predictive dosimetry, an abstract of the risk analysis. We will present you some optimization actions. Then we will have a look at the optimized predictive dosimetry. And after that, we will have a feedback considerations. And we will show you innovations and optimization. The EDF requirements for maintenance operation with strong stakes. The Radiation Protection Department of each nuclear power plant writes a thorough analysis of optimization in collaboration with the provider. The goal is to identify the contributing elements to the collective dose, such the source dose, the radiation protection actions, and their quantified performance. The Nuclear Production Division requirements in radiation protection optimization of the workers is taken into account from the design stage. Each step into the design stage, technical specification, call for tender, technical documents from the provider is analyzed by a radiation protection specialist, which is called PCR in French. The organization for the ALARA principle. First, the radiological context and the objective of those are supplied in a document setting out EDF specifications. From the beginning of the call for tender, the admissibility criteria are considered according to the ALARA principle by the UTO RPS. UTO is Technical Operation Unit. The offered technical documents are analyzed by the RPS considering radiological risk identification, provisional dosimetry, initial and optimized, including the intervention times, the dose limits, and dose mapping. Relevance of optimization actions considered and the dosimetry gains. In situ organization involving the bidder RPS. The in situ organization and the radiological risk optimization actions are validated in the UTO Decision Committee of Risk Prevention before presentation in the Nuclear Power Plant ALARA Committee. And finally, the equipment's qualification done outside the radiological zone is observed and checked by the UTO RPS. During the qualification, the holder must have integrated the radiological risks. How is it declined in the nuclear power plant? The optimization action written in the holder's technical document are transcribed in the ALARA presentation, and the nuclear power plant organized the ALARA committee for the strong stake interventions. The holder RPS, the NPP ALARA RPS, and the management representative have to be here. The UTO contract holder and the RPS UTO are invited. The holder RPS shows the provisional optimized dose and the actions needed for the optimization. The collective dose takes into account the unique radiological state where the work site will be, and all members of ALARA committee validate the actions according to their feasibilities. These actions are written in a report. And what is important is that if one action could not be realized during the intervention, this change has to be justified and validated by the nuclear power plant direction.
Hello everybody. It's a version of replacement of heater wells. Okay, in the first time, we cut the weld. We cut the weld to change the heater, and we come weld two weld here, and here to ajouter, je sais plus comment on dit, intermediate weld to prolong the life of heater weld.
These heaters are inserted into the bottom of the pressurizer.
Donc, in the first time, we install the radiological shielding with a platform, with her platform. In the second time, we disconnect of wire, electrical wire. Then the heater's replacement. Donc, we install our materials to work in the workspace. We machine heater welds here to prepare in the first time to cut the heater and to prepare the first weld. When we cut whole heater, we cutting the heater in some pot to send this heater in the concrete holes, and he go in nuclear déchets. When we cut all the heater, we work in a free time. In the morning we do a Foucault current control to expect the internal welds. The afternoon we welding the intermediate welds, and the night we do a radiographic control. No, when we finish that and the radiographical control is good, we do the electrical reconnection, and we move the radiological shielding, and we do the power test.
The initial predictive dosimetry, the basic assumptions were it was an activity of replacement of 50 rods and installation of 50 intermediate sleeves, mobilization and electrical disconnection. The pressurizer has to be empty. The use of teleoperated machines, and a complete logistic shift was gathered. For the phase of interventions in itself, the estimated collective dose was 125 men millisieverts, and for the logistics it was 11 men millisieverts. So it gives a total of 136 men millisieverts. That is higher than 20 men millisieverts. It shows that this activity is a strong radiological stake. A little abstract on the risk analysis. For the risk of external exposure of the workers, which is a high-level risk, the safeguards were specific radiological shield under the pressuriser, encompassing pressuriser, expansion piping, automated tools, improved pre-job briefings and awareness for evacuation of waste bags, and teledosimetry during sensitive phases, rods cutting and scrapping. For the internal exposure of the worker, which is a significant level risk, the workers will have to wear reinforced ventilated sealed uniforms. Aerosol detectors at the exit of airlocks were placed at the exit of airlocks, decontamination of roads with wipes, and setting up of depression machines as close as possible to the source of contamination. And for the dissemination of contamination risk, which is high-level risk, the safeguards are decontamination of the airlock after each scrapping shift, aerosol detectors are at the exit of airlock, and opening the manhole of the pressuriser as soon as possible to dry the bottom of the pressuriser. The actions of optimization. The use of a specific radiological shield had an estimated dose cost of 5.60 man-millisieverts and an estimated dose gain of 42 man-millisieverts. The use of teledosimetry has an estimated dose cost negligible. The gain is on the time, so it's difficult to put a figure on it. The decontamination of roads with wipes has costs and gains strongly dependent on the dose rates of the roads, and the gain is on the risk of contamination during the scrapping phase. The cost of the use of an automated machine is negligible. The estimated gain is of 50 man-millisieverts, but this gain was initially included in the predictive dosimetry. Using the automatic scrapping machine, so another automated machine has a gain estimated of 30%, and the use of specific reinforced ventilated sealed uniforms. The cost is null if recontamination risk is avoided by helping the workers to undress, and the gain is on the risk of contamination of the workers. The gains, we will see that the gains here are pessimists. Here we have the comparison between the initial predictive dosimetry, the optimized predictive collective dose, and the real dose that was taken by the workers. We see that for the intervention phases, the initial predictive dosimetry was 125 man-millisieverts, and finally it was 44 man-millisieverts. The total cost, dosimetry cost, was 54 man-millisieverts in regards of the 136 that were estimated at the beginning. So the gain in the dosimetry of the workers is finally of 82 man-millisieverts regarding the initial predicted dosimetry. Now Jonas will present you the innovations.
It's an intervention we've done for many years now, and we have more than 25 years of feedback. So this feedback is applied to many parts of the intervention. The first one is the equipment. We have developed and improved other equipments to integrate the ALARA principle, and absolutely all our equipment now is teleoperated. On the right picture, you can see the machine which is used to cut in several parts the heater once removed of the pressuriser. The working environment is a key part of the intervention because we have to prevent the spread of the contamination outside of the room of the pressurizer. So we mount reinforced airlocks designed to that. You can see on the left the room, which is fully covered of plastic to prevent the contamination to be spread in the floors. The organization on site has changed for years, and now we have optimized all the activity sequences. And for example, we do the non-destructive controls during the night, the radiological shootings, which was impossible before because we have coactivity and we had to do that in the morning. So now, to impact less the other workers in the reactor building, we do that on the night. Some of the sequences of the intervention are independent of the number of heaters we remove. So if we remove 1 or 30 heaters, we have to do that. For example, the setup of the radiation shielding, the mobilization of the equipment. So to integrate less dosimetry, we now replace half a pressurizer instead of 1/3. It's a dosimetry gain for all our workers. The management of the integrated dosimetry has changed through the years. We have many tools now, just like teledosimetry, to manage and handle better the dosimetry taken by our workers. Thanks to this feedback, we have some innovations we have developed over the years. The first one is we use specific radiological waste bags, as you can see on the left, on our tools, because the common ones are not designed to that, and we have better optimization of the time of the intervention with our bags. We have a specifically designed radiological shield on the right, on the picture on the right. We set up when we arrive on site. Every equipment is teleoperated. We use, for example, reinforced ventilated seal uniforms because the common ones sometimes crack when we use them because the area of the pressurizer is very small. And the logistical staff is very important for this intervention because it's a key part to prevent the spread of the contamination. So we doesn't use the staff of the nuclear power plant. We have our own crew to set up the logistic of all the intervention. All this dosimetry innovation and optimization allowed us to have a gain around 30% from 2006 to these days. As you can see on the graph, we have a very higher average collective dosimetry in 2015 and 2016, but it's mainly because the radiological context of the intervention is very random when we intervene, depending on the nuclear power plant we are on. But nonetheless, we have a good dosimetry gain. Thank you very much.